Introduction to Merkle trees. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are going to explore one of the most elegant and powerful data structures in computer science, the Merkle tree. Named after Ralph Merkle, who patented it in 1979, this structure has become fundamental to blockchain technology, distributed systems, and data verification. You might wonder why a data structure from the 1970s is still so relevant today. The answer lies in its brilliant simplicity and efficiency. Merkle trees solve a critical problem. How do you verify the integrity of large amounts of data without actually having to download or process all of it? In this presentation, we'll break down exactly how Merkle trees work, why they're so important in blockchain and distributed systems, and how they enable everything from Bitcoin transactions to Git version control to peer-to-peer file sharing. Whether you are a developer, blockchain enthusiast, or just curious about data structures, understanding Merkle trees will give you insight into one of the core technologies powering modern distributed systems. What is a Merkle tree? Let's start with the fundamentals. A Merkle tree, also known as a hash tree, is a tree data structure where every leaf node contains a cryptographic hash of a data block, and every non-leaf node contains a hash of its child nodes. Think of it like a family tree, but instead of names, each node contains a hash value. The leaves at the bottom represent your actual data, and as you move up the tree, each parent node summarizes its children through hashing. At the very top of the tree is a single hash, called the Merkle root or root hash. This hash value represents all the data in the entire tree. It's like a fingerprint for your entire dataset. The beauty of this structure is that if any single piece of data changes at the bottom of the tree, the change propagates upward through all the parent hashes. This ultimately changes the root hash. This makes tampering immediately detectable. In their most common form, Merkle trees are binary trees, which means each non-leaf node has exactly two children. This binary structure provides optimal efficiency for verification proofs, which we will explore in detail later. How Merkle trees work. Let's walk through the construction of a Merkle tree step by step with a concrete example. Imagine we have 4 data blocks that we want to organize into a Merkle tree. Block A, Block B, Block C, and Block D. First, we hash each data block individually using a cryptographic hash function like SHA-256. This gives us hash A from Block A, hash B from Block B, hash C from Block C, and hash D from Block D. These 4 hashes become our leaf nodes. Next, we pair up adjacent leaf nodes and hash them together. We concatenate hash A and hash B, then hash the result to create hash AB. Similarly, we concatenate hash C and hash D and hash them to create hash CD. Now we have 2 nodes at the second level. Finally, we take these 2 second-level hashes, concatenate hash AB and hash CD together, and hash the result. This produces our Merkle root, hash ABCD. This single hash represents all 4 original data blocks. The process is recursive and works for any number of data blocks. If you have 8 blocks, you'd create 8 leaf hashes, combine them into 4 parent hashes, then 2, then 1. The tree grows upward from the data, always reducing by half at each level until you reach the single root. Tree construction example. Let's make this even more concrete with actual example data. Suppose we have 4 transactions in a blockchain block, and we want to create a Merkle tree to represent them efficiently. Transaction A might be Alice sends 5 BTC to Bob. Transaction B is Charlie sends 2 BTC to David. Transaction C is Eve sends 3 BTC to Frank. And transaction D is Grace sends 1 BTC to Henry. These are our 4-leaf data points. We apply SHA-256 to each transaction. The actual hash values would be long hexadecimal strings, but for illustration, let's say we get hash A, hash B, hash C, and hash D. These are our leaf nodes positioned at the bottom of the tree. Moving up one level, we concatenate hash A with hash B in practice. This means putting the two hash values end to end as a single string, then hashing that combined string. This produces hash AB. We do the same with hash C and hash D to produce hash CD. For the final level, we concatenate hash AB and hash CD, then hash the result one more time. This gives us the Merkle root. This root hash is stored in the blockchain block header and serves as a compact representation of all four transactions. What's remarkable is that this single root hash, typically just 32 bytes for SHA-256, can represent millions of transactions while still allowing efficient verification, as we'll see shortly. Properties of Merkle trees. Merkle trees have several key properties that make them so useful in distributed systems and blockchain technology. Understanding these properties helps explain why they are chosen over simpler alternatives. First, they provide efficient verification. To prove that a specific data block is part of the tree, you do not need the entire tree. You only need a logarithmic number of hashes. For a tree with 1 million leaf nodes, you would only need about 20 hashes to prove membership. Second, they ensure data integrity. Any modification to a leaf node changes its hash. This then changes its parent's hash, and that change propagates all the way up to the root hash. This makes tampering detectable without checking every single data block. Third, they're deterministic. Given the same set of data blocks in the same order, you will always get the same Merkle root. This consistency is crucial for distributed systems where multiple parties need to agree on data validity. Fourth, they enable efficient comparison. Instead of comparing entire datasets, two parties can simply compare Merkle roots. If the roots match, the datasets are identical. If they differ, you can quickly narrow down which specific data blocks are different. Finally, Merkle trees are space efficient for verification. Instead of storing or transmitting entire datasets, you can work with just the root hash and verification paths, dramatically reducing storage and bandwidth requirements. Merkle proofs. Now let's explore one of the most powerful features of Merkle trees. Merkle proofs, also called Merkle paths or authentication paths. A Merkle proof allows you to prove that a specific piece of data is included in a Merkle tree without revealing the entire tree. Imagine you want to prove that transaction C is part of a Merkle tree whose root is stored in a blockchain. You don't need to provide all the transactions. You only need to provide transaction C itself, along with a minimal set of sibling hashes that allow someone to reconstruct the path to the root. For transaction C in our 4-transaction example, the Merkle proof would consist of 4 components: the hash of transaction C, hash D, C's sibling, hash AB, the sibling of C and D's parent, and the Merkle root for comparison. For transaction C in our 4-transaction example, the Merkle proof would consist of 4 components: the hash of transaction C, hash D, C's sibling, hash AB, the sibling of C and D's parent, and the Merkle root for comparison. The verifier can then hash transaction C to get hash C, combine it with the provided hash D to compute hash CD, then combine hash CD with the provided hash AB to compute the root. If this computed root matches the known root hash, the proof is valid. The beauty of this approach is its efficiency. For a tree with n leaf nodes, a Merkle proof requires only log base 2 of n hashes. So, for 1024 transactions, you need only 10 hashes. For a million transactions, you need only 20 hashes. This logarithmic growth makes Merkle proofs incredibly scalable. Verification process. Let's walk through the complete verification process step by step to really understand how Merkle proofs work in practice. This is where the elegance of the structure becomes apparent. Suppose Alice wants to prove to Bob that a specific transaction is included in a blockchain block. Bob has the block header, which contains the Merkle root, but he doesn't have all the transactions. That would be too much data to download. Alice provides Bob with the transaction in question. Let's call it transaction X, along with a Merkle proof consisting of the sibling hashes needed to reconstruct the path to the root. Alice knows which hashes to provide based on the position of transaction X in the tree. Bob starts by hashing transaction X to get its hash value. Then, he combines this hash with the first sibling hash from the proof, in the correct order based on whether the transaction is a left or right child. He hashes this combination to get the parent hash. Bob repeats this process, moving up the tree level by level. At each level, he combines his current hash with the next sibling hash from the proof and hashes the result. He continues until he reaches the top of the tree and computes a final root hash. Finally, Bob compares his computed root hash with the Merkle root from the block header. If they match exactly, the proof is valid, transaction X is definitely in the block. If they don't match, either the transaction isn't in the block or someone is trying to deceive Bob. This entire verification process requires only logarithmic time and space, making it practical even for mobile devices with limited resources. This is why lightweight Bitcoin wallets can verify transactions without downloading the entire blockchain. Merkle trees in blockchain. Merkle trees are absolutely fundamental to how blockchains work, particularly in Bitcoin and Ethereum. Understanding their role in blockchain helps appreciate why they were chosen and what problems they solve. In blockchain, each block contains potentially thousands of transactions. Storing all these transaction hashes in the block header would make headers enormous and impractical. Instead, all transactions are organized into a Merkle tree, and only the Merkle root is stored in the block header. This design decision has profound implications for scalability. Full nodes that store the entire blockchain need to maintain all transactions and can construct the full Merkle trees. But lightweight nodes, like mobile wallets, only need to download block headers containing Merkle roots. When a lightweight node wants to verify that a specific transaction was included in a block, it doesn't download all transactions. Instead, it requests a Merkle proof from a full node. The full node provides the transaction and the sibling hashes needed to verify it against the Merkle root in the header. This architecture enables simplified payment verification, or SPV, which is how Bitcoin mobile wallets work. An SPV wallet might download only 80-byte block headers instead of megabytes of transaction data per block, yet it can still cryptographically verify that transactions affecting its addresses are included in the blockchain. The security model is elegant. As long as the longest chain is controlled by honest miners, the Merkle roots in the headers are trustworthy, and Merkle proofs allow efficient verification without trusting any single party to provide honest transaction data. Efficiency analysis. Let's dive into the mathematical efficiency of Merkle trees compared to alternative approaches. Understanding the numbers helps explain why Merkle trees are the preferred solution for data verification at scale. Consider a blockchain block with 2048 transactions. If we wanted to prove that one specific transaction is included, the naive approach would be to provide all 2048 transactions so the verifier could check them. With typical transaction sizes, this might be several megabytes of data. With a Merkle tree, we organize these 2048 transactions into a tree with 11 levels. The leaf level plus 10 levels of parent nodes, since 2 to the power of 11 equals 2048. To prove a transaction is included, we only need to provide 11 hashes, one for each level of the tree. Each SHA-256 hash is 32 bytes, so the total Merkle proof size is 11 multiplied by 32, which is 352 bytes. That's compared to potentially megabytes for the naive approach. The savings are dramatic. We've reduced the proof size by a factor of thousands. This efficiency scales beautifully. For 1 million transactions, we would need only 20 hashes in the proof. For 1 billion transactions, only 30 hashes. The logarithmic growth means that even as blocks grow to contain more transactions, verification remains practical. The computational cost is equally efficient. Verifying a Merkle proof requires performing only a logarithmic number of hash operations. Hash functions are fast. Modern processors can compute millions of SHA-256 hashes per second. So even resource-constrained devices like smartphones can verify Merkle proofs in milliseconds. Comparison with alternatives. To truly appreciate Merkle trees, it is helpful to compare them with alternative approaches to data verification. Each alternative has drawbacks that Merkle trees elegantly avoid. The simplest alternative is storing a list of all hashes. In a blockchain block, you could store a hash for every transaction in the block header. This allows verification by checking if a transaction's hash appears in the list. However, this scales linearly. For example, a block with 10,000 transactions would need a header with 10,000 hashes, making headers huge. Another alternative is hashing all data together into a single hash. You could concatenate all transactions and hash them once to get a single digest for the block. This gives you a compact representation, but verification becomes impossible without having all the data. To verify one transaction, you would need all transactions, defeating the purpose of efficient verification. A third approach is using signatures or checksums on individual data blocks without a tree structure. This allows verification of individual blocks but does not provide a single root hash representing the entire dataset. You cannot efficiently prove that your block is part of a specific larger dataset. Merkle trees combine the best aspects of all these approaches. You get a single compact root hash representing all data, yet you can efficiently prove that any specific data block is included in the set. The logarithmic scaling of proof size is the key advantage that alternatives lack. This is why Merkle trees appear not just in blockchain, but in distributed file systems, version control systems, and databases. They are simply the best known solution for efficient, verifiable data summarization. Merkle trees in Bitcoin. Let's examine how Bitcoin implements Merkle trees, since this is one of its most important real-world applications. Bitcoin's design showcases both the elegance and practical considerations for using Merkle trees at scale. In Bitcoin, every block contains a Merkle tree of all transactions in that block. The block header, which is exactly 80 bytes, includes 6 fields: version, previous block hash, Merkle root, timestamp, difficulty target, and nonce. The Merkle root takes up 32 of those 80 bytes. Bitcoin blocks can contain anywhere from one transaction to several thousand. The Coinbase transaction, which creates new bitcoins for the miner, is always the first transaction. All other transactions in the block are organized with the Coinbase transaction into a complete Merkle tree. When constructing the tree, Bitcoin hashes each transaction using double SHA-256, meaning it hashes the result of SHA-256 again with SHA-256. This double hashing provides an extra security margin. The tree is built bottom-up, repeatedly pairing and hashing until only the root remains. If the number of transactions is odd at any level, Bitcoin duplicates the last transaction hash to make an even number. This ensures the tree structure remains binary. For example, with 5 transactions, the 5th transaction hash is duplicated so there are 6 leaf nodes, which can be paired properly. SPV clients in Bitcoin, which include most mobile wallets, download only block headers. When such a client needs to verify a transaction, it requests a Merkle proof from full nodes. The full node provides the transaction and the minimal set of hashes needed to compute the path to the Merkle root in the header the client already has. This architecture is why Bitcoin can scale to lightweight clients that run on phones with limited storage and bandwidth, while still providing cryptographic security guarantees that transactions are included in the blockchain. Merkle trees in Ethereum. Ethereum takes the Merkle tree concept even further than Bitcoin, using not just 1 but 3 different Merkle trees in every block. This more complex design serves Ethereum's needs as a distributed computer, not just a currency. The first tree is the transaction tree, similar to Bitcoin's. It contains all transactions in the block organized into a Merkle tree. The transaction root in the block header represents all these transactions. The second tree is the receipts tree. In Ethereum, executing a transaction produces a receipt that contains information about the transaction's execution, including logs emitted by smart contracts. These receipts are organized into their own Merkle tree, with the receipts root stored in the block header. The third tree is the state tree, which is the most innovative. Ethereum maintains a world state, essentially a key-value database mapping addresses to account states. This entire state is organized into a Merkle tree, and the state root is included in every block header. This allows proving what any account's balance or storage was at any point in history. Ethereum actually uses a variant called a Merkle-Patricia tree, which combines a Merkle tree with a Patricia tree data structure. This provides efficient updates and lookups while maintaining the verifiability properties of Merkle trees. It's optimized for Ethereum's need to frequently update the state tree as transactions modify account balances and smart contract storage. The three roots in Ethereum's block header, transaction root, receipts root, and state root, enable what Ethereum calls light client protocol. Light clients can verify not just transaction inclusion like Bitcoin, but also verify the results of smart contract execution and query historical account states, all with Merkle proofs. Beyond blockchain applications. While Merkle trees are famous in blockchain, they are used in many other distributed systems and applications. Understanding these other uses shows the versatility of this data structure. Git, the version control system used by millions of developers, uses Merkle trees to efficiently represent repositories. Each commit in Git contains a tree object that is essentially a Merkle tree of all files in that commit. This allows Git to efficiently detect changes between commits and verify repository integrity. Peer-to-peer file sharing protocols like BitTorrent use Merkle trees to verify downloaded chunks. When you download a large file from multiple peers, each chunk can be verified against a Merkle tree root. This prevents malicious peers from providing corrupted data without requiring trust in any single peer. Distributed databases like Apache Cassandra use Merkle trees for anti-entropy repairs. When replicas of data might have diverged, nodes exchange Merkle roots to quickly identify which data ranges differ, then sync only those ranges instead of comparing entire datasets. Certificate transparency, a system for monitoring secure sockets layer certificates, uses Merkle trees to maintain append-only logs of all issued certificates. This allows anyone to verify that a certificate was properly logged and detect misissued certificates without trusting the certificate authorities. Cloud storage systems use Merkle trees to efficiently verify data integrity. When you upload files to cloud storage, the service can organize them into Merkle trees, allowing efficient verification that your files haven't been tampered with or corrupted without downloading everything. The common thread across all these applications is the need to efficiently verify data integrity in distributed systems where you can't trust all participants or where downloading everything is impractical. Merkle trees solve this problem elegantly across all these domains. Security considerations. While Merkle trees provide strong security guarantees, it is important to understand both their strengths and potential vulnerabilities. Proper implementation requires attention to several security considerations. The security of a Merkle tree fundamentally depends on the cryptographic hash function that is used. If that hash function has weaknesses, the entire structure becomes compromised. Bitcoin uses SHA-256, which is considered secure. However, if SHA-256 were ever broken, meaning attackers could find collisions efficiently, Merkle trees that use it would then be vulnerable. One potential attack is the second preimage attack. If an attacker can find a different input that produces the same hash as a legitimate data block, they could substitute malicious data. However, good hash functions like SHA-256 make this computationally infeasible. It would take billions of years with current technology. Another consideration is the distinction between leaf nodes and internal nodes. Some implementations hash leaf nodes differently from internal nodes to prevent certain attacks. Without this distinction, an attacker might craft a proof that makes an internal node appear to be a leaf, potentially fooling verifiers. The order of data within the tree is also important for security. For example, in Bitcoin, transactions have a specific order within the block, and this order determines the tree's structure. If the order changes, the root also changes. Therefore, verifiers must ensure that the order is correct. Some systems use sorted Merkle trees, where data is arranged in a canonical order. This prevents attacks related to data ordering. Finally, the tree construction must handle edge cases properly. What happens with an odd number of leaves? What about a tree with just one transaction? Bitcoin duplicates the last hash to make pairs, which is safe, but naive implementations might have vulnerabilities if edge cases aren't handled correctly. Despite these considerations, when implemented properly with a strong hash function, Merkle trees provide excellent security guarantees. The cryptographic properties ensure that tampering is detected and verification is trustworthy. Variants and extensions. The basic Merkle tree we have described has inspired several variants and extensions that adapt the structure for specific use cases. These variants maintain the core benefits while adding new capabilities. Merkle Patricia trees, which Ethereum uses, combine Merkle trees with Patricia tries. This structure is optimized for key-value storage where you want to prove both inclusion and the key-value mapping efficiently. It is particularly useful when the tree needs frequent updates, as in Ethereum's state tree. Sparse Merkle trees are designed for very large key spaces where most potential keys are empty. Instead of only including present keys, a sparse Merkle tree has a position for every possible key, with empty positions having a default hash. This allows proving non-inclusion, that a key is definitely not in the tree, which standard Merkle trees cannot do efficiently. Merkle mountain ranges, used in some blockchain systems like Grin, are append-only structures optimized for adding new data without recomputing the entire tree. They consist of multiple perfect binary trees of decreasing sizes, making them efficient for blockchains where new blocks are constantly added. Merkle trees are a newer variant that uses vector commitments instead of hash functions. They can provide much smaller proof sizes than traditional Merkle trees, potentially constant size regardless of tree depth. Ethereum is considering Merkle trees for future upgrades to reduce the data light clients need. Authenticated data structures combine Merkle trees with other structures like skipped lists or balanced trees. These allow not just membership proofs but also range queries and ordering proofs, useful in database systems that need to prove query results. Each variant trades off different properties. Standard Merkle trees are simple and widely understood. More complex variants offer benefits like smaller proofs, non-inclusion proofs, or efficient updates, but at the cost of increased complexity and sometimes weaker security assumptions. Performance characteristics. Let's analyze the performance characteristics of Merkle trees across different operations. Understanding the computational costs helps in choosing when and how to use them effectively. Tree construction time is linear in the number of leaves. If you have n data blocks, you need to compute n hashes for the leaf level, then n divided by 2 hashes for the next level, then n divided by 4, and so on. The total is approximately 2 n hash operations, which is O of n complexity. For Bitcoin blocks with thousands of transactions, this takes just milliseconds on modern hardware. Verification time for a Merkle proof is logarithmic. To verify one element, you perform log base 2 of n hash operations, one for each level of the tree. Even for 1,000,000 leaves, this is only 20 hash operations. Since SHA-256 computation is extremely fast, verification typically takes microseconds. Proof size is also logarithmic. A proof consists of log base 2 of n hashes, each 32 bytes for SHA-256. This means proof sizes are very small. For 1,000,000 leaves, only 640 bytes. This is why Merkle proofs work well even on mobile networks with limited bandwidth. Update cost depends on the implementation. For an append-only structure like blockchain, adding new data means constructing a new tree, which is big O of n. However, for updatable structures like Merkle-Patricia trees, you can update just the path from the changed leaf to the root, which is big O of log n. This makes them suitable for frequently changing datasets. Space requirements are linear. The tree stores n leaf hashes and approximately n internal node hashes, for a total of about 2 n hashes. For storage-constrained systems, you can store only the leaves and recompute internal nodes on demand, trading computation for storage. These performance characteristics make Merkle trees practical for real-world use. The logarithmic verification is the key property that enables scalable distributed systems. Implementation considerations. When implementing Merkle trees in software, several practical considerations affect correctness, security, and performance. Let's explore the key implementation details that developers need to get right. First, choosing the hash function is critical. SHA-256 is the most common choice, offering strong security and good performance. Some systems use SHA-3 or Blake2 for different security performance trade-offs. The hash function must be collision-resistant and preimage-resistant to ensure security. Handling concatenation order matters. When combining two child hashes, should the left child come first or the right? You must be consistent and document the choice. Bitcoin always puts the left child first. Inconsistent ordering would produce different roots for the same data, breaking verification. Leaf node prefixing is a security best practice. To distinguish leaf hashes from internal node hashes, many implementations prepend a byte to the data before hashing. For example, 0x00 for leaves and 0x01 for internal nodes. This prevents attacks where internal nodes are presented as leaves. Managing odd numbers of leaves requires careful handling. The common approach involves duplicating the last hash when an odd number is present at any level. Alternatively, you can promote odd nodes to the next level without pairing. Both methods work, but consistency is crucial. Storing the tree efficiently matters for performance. You can use an array-based representation where node I has children at 2i and 2i plus 1, similar to binary heap implementations. Alternatively, you can use explicit node objects with pointers. Array representation is more cache-friendly for smaller trees. Generating Merkle proofs requires tracking the path from a leaf to the root and collecting sibling hashes at each level. The proof must also include information about whether each sibling is a left or right child, as this affects the concatenation order during verification. These implementation details might seem minor, but getting them wrong can lead to security vulnerabilities or incompatibility with other systems. Following established patterns and thoroughly testing edge cases is essential. Real-world use cases. Let us examine concrete real-world scenarios where Merkle trees solve practical problems. These examples demonstrate why the theoretical benefits translate to actual value in deployed systems. In Bitcoin's SPV wallets, mobile users can verify transactions without downloading gigabytes of blockchain data. The wallet downloads only 80-byte headers, about 50 megabytes for the entire blockchain history. When a transaction arrives, the wallet requests a Merkle proof from full nodes. Within seconds, with just kilobytes of data, the wallet cryptographically verifies the transaction is in the blockchain. In IPFS, the interplanetary file system, large files are split into chunks and organized into Merkle trees, called Merkle DAGs, or directed acyclic graphs. When you share a file, you share its root hash. Others can download chunks from multiple sources and verify each chunk against the Merkle tree, ensuring data integrity without trusting any single source. In Amazon DynamoDB and other distributed databases, Merkle trees enable efficient replica synchronization. When replicas suspect they are out of synchronization, they exchange Merkle tree roots. If roots match, the replicas are identical. If not, they recursively compare subtree roots to pinpoint exactly which data ranges differ, then synchronize only those ranges. In certificate transparency logs, which monitor all secure sockets layer certificates issued by certificate authorities, Merkle trees provide append-only guarantees. Certificate authorities must submit certificates to public logs. Anyone can verify a certificate was logged by requesting a Merkle proof. The append-only property, enforced by Merkle trees, prevents authorities from later removing evidence of misissued certificates. In secure boot systems, device firmware is organized into Merkle trees. The bootloader verifies the root hash against a trusted value, then verifies components as they load using Merkle proofs. This ensures only authorized firmware runs, even if storage is compromised. These use cases span finance, file sharing, databases, security infrastructure, and embedded systems, demonstrating that Merkle trees are truly a fundamental building block of modern computing infrastructure. Advantages and limitations. To use Merkle trees effectively, it's important to understand both their strengths and limitations. No data structure is perfect for every situation, and Merkle trees are no exception. The primary advantage is efficient verification. Logarithmic proof sizes mean that you can verify data in large datasets without downloading everything. This is transformative for mobile and resource-constrained devices that need to participate in distributed systems. Another advantage is integrity guarantees. The cryptographic properties ensure that any tampering is detected. You can't change data without changing the root hash, providing strong assurance that data hasn't been modified. Merkle trees also enable efficient synchronization between replicas in distributed systems. By comparing roots and recursively checking subtrees, you can quickly find discrepancies without comparing entire datasets. This is crucial for maintaining consistency across distributed replicas. However, Merkle trees have limitations. They're designed for static or append-only data. Frequently updating elements in the middle of the tree requires reconstructing large portions, which can be expensive. Variants like Merkle Patricia trees address this but add complexity. Another limitation is that standard Merkle trees can only prove inclusion, not exclusion. You can prove a data block is in the tree, but proving something is not in the tree requires providing much more information. Sparse Merkle trees solve this but with higher overhead. Merkle trees also require careful implementation to avoid security pitfalls. Issues like second preimage attacks, leaf node confusion, and improper handling of edge cases can introduce vulnerabilities if developers are not careful. Finally, Merkle trees provide no privacy. They reveal the structure and hashes of data. For applications requiring privacy, techniques like zero-knowledge proofs or encrypted Merkle trees add complexity and overhead. Understanding these trade-offs helps in deciding when Merkle trees are appropriate and when alternative structures might be better suited. Future of Merkle trees. As we conclude our deep dive into Merkle trees, let's look at how they are evolving and what the future might hold for this fundamental data structure. Post-quantum cryptography is an active area of research. Current Merkle trees rely on hash functions like SHA-256, which quantum computers cannot break efficiently. However, as public key cryptography moves to quantum-resistant algorithms, Merkle signature schemes are being developed as quantum-resistant alternatives to traditional signatures like ECDSA. Merkle trees represent a potential evolution in blockchain systems. By using vector commitments instead of traditional hashing, they can provide constant size proofs regardless of tree depth. Ethereum is exploring Merkle trees to reduce the data requirements for stateless clients, potentially enabling even lighter wallets. Zero-knowledge Merkle trees combine Merkle trees with zero-knowledge proofs, allowing you to prove properties about data without revealing the data itself. For example, you could prove your balance exceeds a threshold without revealing the exact amount. This combines efficiency with privacy. Cross-chain interoperability protocols use Merkle trees to enable communication between different blockchains. Merkle proofs from one chain can be verified on another, allowing atomic swaps and bridging assets between chains in a trustless manner. As distributed systems continue to grow and blockchain technology matures, the fundamental problems that Merkle trees solve, efficient verification, data integrity, and trustless synchronization, remain critical. The specific implementations may evolve, but the core concepts will continue to be relevant. Whether you're building blockchain applications, distributed databases, peer-to-peer systems, or any application requiring verifiable data structures, understanding Merkle trees gives you a powerful tool for solving scalability and trust problems. Thank you for your attendance. Please consider subscribing to the channel.